There is a vertebra in a museum drawer that weighs more than a cinder block. It is pale, the color of old bone left in desert sun. The surface is porous, rough to the touch, textured like dried coral. If you run your finger along the ridges, you can feel where the mineral replaced what was once living tissue. Sand is still embedded in some of the crevices, grains from an ancient seabed locked into stone 40 million years ago. This is not the bone of a dinosaur. It is far younger than that. It is not the bone of a crocodile, though it was first mistaken for one. It is the vertebra of a whale that lived when the world was greenhouse warm, when ice did not yet cling to the poles, when shallow seas drowned the coasts of continents that would one day be named Alabama, Egypt, Pakistan. The museum is quiet. The fossil sits among others, labeled, cataloged, a fragment of a skeleton that was once 60 feet long. Basilosaurus cedoides. King lizard. The name is a mistake, coined in the 1830s by men who thought they had found a marine reptile, some cousin to the mosasaurs of the Cretaceous. But bones do not lie for long. The teeth told the truth. Mammalian. Differentiated. Sharp at the front for seizing, serrated at the back for cutting. This was no reptile. The vertebra is heavy because time has made it so. Calcium phosphate has replaced the collagen and marrow. What was flexible is now stone. What once flexed with the rhythm of a living spine now rests motionless in controlled climate, behind glass or in storage. A relic of an ocean that no longer exists. Outside the museum, the sun is bright. Inside, the air is still. The fossil waits. It has been waiting for a very long time. Imagine a school bus. 40 feet, perhaps 50. Now stretch it. Add another 10 feet. Make it narrower. Taper the body like a ribbon. This is the shape of Basilosaurus. The skull alone was as long as a kayak. 3 feet, maybe more. The jaws held teeth that could puncture through blubber and bone. The front teeth were conical, built for gripping. The back teeth were triangular, serrated, designed to saw through flesh. A carnivore. An apex predator. But not a monster. Just an animal. Hungry. Efficient. Alive. The body was serpentine, in a way no modern whale is. Most whales today are built like torpedoes, compact and streamlined. Basilosaurus was different. Its spine was elongated, each vertebra stretched, creating a body that undulated through the water like a living eel. The ribs were dense, pachystotic, weighted to help with buoyancy control in shallow seas. At the end of that long body was a tail. Not quite the tail of a modern whale, but something approaching it. A fluke horizontal for vertical propulsion. Basilosaurus swam by moving its spine up and down, not side to side like a fish. Mammalian locomotion. Inherited from ancestors that once walked on land. And buried in the pelvis, tiny and vestigial, were hind limbs. Legs. Too small to be functional, but there. Evolutionary memory. Evidence of a lineage that had, millions of years before, left the land and returned to the sea. Picture it moving. Not thrashing. Not frantic. Slow, powerful strokes. A ribbon of muscle and bone gliding beneath the surface, rising only to breathe. The exhalation sharp and wet, a mist in warm air, then descent again into the blue-green haze of an Eocene sea. It is easy to imagine Basilosaurus as something sinister. The name does not help. King lizard. serpentine body, teeth like daggers. The mind reaches for dragons, for sea monsters, for the leviathans of myth. But this is projection. Basilosaurus was not cruel. It was not evil. It was a mammal, warm-blooded, with a four-chambered heart that pumped oxygenated blood through arteries and veins. It had lungs. It surfaced to breathe. It gave birth to live young. It nursed its calves with milk rich in fat. Imagine a mother and calf in shallow water. The calf is small, perhaps 12 feet long, still learning to dive, still dependent. The mother circles, slow, watchful. She is not thinking. Not in the way we think. But she is aware. Her brain, though smaller than a modern sperm whale's, is complex enough for spatial memory, for recognizing her young, for responding to distress. When Basilosaurus hunted, it did so out of necessity, not malice. Hunger is not a moral failing. It is a biological imperative. The whale needed thousands of calories a day to maintain its body temperature, to fuel its metabolism. It hunted because it had to. It killed because that is what carnivores do. There is no villain in the fossil record. Only animals doing what they evolved to do. Survival. Reproduction. The continuation of genes across generations. Basilosaurus was not a monster. It was a whale. A very old whale. A very dead whale. But once, for a span of several million years, it was the dominant predator in warm, shallow seas. And then it was not. We will leave the museum now. The fossil will remain. It has nowhere else to go. But we can move. We can step out of the present, out of the world of glass cases and climate control, and walk backward through time. The transition will not be sudden. There is no portal, no flash of light. Instead, imagine the museum walls dissolving like mist. The floor beneath your feet softens, becomes sand, becomes silt. The air warms. The ceiling opens to sky. The light changes. No more fluorescent hum. Just sunlight, direct and heavy, the kind of light that exists only in greenhouse climates. We are going to the late Eocene, 37 million years ago. A time when the continents were almost where they are now, but not quite. When the Atlantic was narrower. When India had only recently collided with Asia. When Antarctica was just beginning to drift toward the pole. We are going to a coastline that does not exist anymore. To a sea that has long since drained away. To a world where Basilosaurus still swims. But before we arrive, we must understand how we know it existed at all. Welcome to Info Jungle. If you enjoy calm, thoughtful documentaries about the natural world, consider subscribing. These videos are created to help you relax while learning at a gentle pace. The first bones of Basilosaurus were found in the 1830s in the chalk hills of Alabama. The American South was still a raw frontier then, and the hills were being carved open for farmland and roads. Workers found the bones embedded in sediment that had once been ocean floor. The fossils were enormous, serpentine, articulated in long chains like the spine of a snake. A physician named Richard Harlan examined the remains. He saw the elongated vertebrae, the conical teeth, and made an assumption: reptile. He named it Basilosaurus, the king lizard, and published his findings in 1834. The name caught. Newspapers ran stories about the discovery of a sea serpent. The bones were put on display. Curiosity became spectacle. But then Richard Owen entered the picture. Owen was meticulous. He examined the skull. He noted the differentiated teeth, incisors, canines, premolars, molars. Reptiles do not have differentiated teeth. Mammals do. He looked at the inner ear bones. Mammalian. He studied the vertebrae more carefully. Mammalian structure. No doubt. In 1839, Owen reclassified Basilosaurus as a mammal, specifically a whale. He proposed renaming it Zeuglodon, meaning yolk tooth, a reference to the distinctive shape of the molars. But the rules of taxonomy are unforgiving. The first name published holds priority. Basilosaurus, the incorrect name, remained. Over the following decades, more specimens were found, not just in Alabama, but in Louisiana, Arkansas, Mississippi. In Egypt, near the Fayum Depression, where desert winds exposed ancient seabeds. In Pakistan, in the sediments of Tethys, the great tropical ocean that once separated Africa and Eurasia. Each skeleton told the same story. This was a whale, a primitive whale, still carrying the anatomical echoes of terrestrial ancestry. The pelvis was larger than in modern whales. Fused to it were tiny, functionless hind limbs. Femur, tibia, even remnants of feet. Too small to aid in locomotion. Too small to matter. But present. This was proof of transition. Evidence that whales had not always been aquatic. That they had descended from four-legged mammals that walked on land. That evolution was not theory but fact, written in bone. The question that haunted paleontologists was simple. Why did a whale have legs? The answer is deep time. Millions of years deep. Basilosaurus was not the first whale. It was a descendant of whales that had already been aquatic for millions of years. Its ancestors, Pachycetus ambulocetus rodhostis, were amphibious, semi-aquatic, experimenting with life in the water. With each generation, the limbs became less necessary. The spine became more flexible. The tail became more powerful. Natural selection favored traits that improved swimming, not walking. By the time Basilosaurus emerged, 37 million years ago, the legs were vestigial. Useless for propulsion. Possibly used in mating, perhaps for gripping or positioning. Or perhaps for nothing at all. Just remnants. Genetic inertia. The body's reluctance to fully let go of what it once was. The discovery of Basilosaurus did more than add a species to the fossil record. It revealed the plasticity of life. The way organisms are shaped by their environments over incomprehensible spans of time. The way the past persists in the present, encoded in bone, waiting to be read. To understand the world of Basilosaurus, we must first understand the modern ocean. Because the Eocene seas were not so different. Warmer, yes. Shallower in places. But still salt water. Still governed by the same physics, the same chemistry, the same relentless pressure to adapt or die. Today in tropical waters, there are still warm, shallow seas. The Caribbean, the Gulf of Mexico, the coastlines of Southeast Asia. These are refuges for life that requires heat and light. Coral reefs thrive here. Mangroves line the shores. Fish schools move in synchronized patterns, avoiding predators, seeking plankton blooms. Modern whales inhabit these waters. Not the great baleen whales of the polar seas, but toothed whales. Orcas. Pilot whales. Dolphins. They are compact, muscular, built for bursts of speed. They hunt cooperatively. They communicate with clicks and whistles. Their brains are large, capable of complex social behavior. Basilosaurus was not like this. It was solitary, or at most lived in small groups. Its brain was smaller, less convoluted. It did not echolocate, or if it did, the structures were primitive. It hunted by sight, by scent, by the pressure-sensitive cells along its jaw that could detect movement in the water. But the act of swimming, this was similar. A modern whale moves through water by flexing its spine, driving its tail fluke up and down. Basilosaurus did the same. The elongated body gave it a different rhythm. More undulation, less explosive power. But the principle was identical. Vertical flexion, mammalian locomotion. Watch a humpback whale glide beneath the surface. The way it moves is slow, deliberate, almost weightless. Now stretch that body. Make it longer, narrower. Remove some of the bulk. Add more vertebrae. This is Basilosaurus. Not alien, just different. A variation on the same evolutionary theme. The Eocene ocean was warmer than today's ocean. Significantly warmer. Global temperatures were 5 to 8 degrees Celsius higher than the present. There were no ice caps at the poles. Sea levels were higher, flooding continental shelves, creating vast shallow seas. This warmth created a greenhouse world. Tropical conditions extended far into what are now temperate zones. Crocodiles lived in Greenland. Palm trees grew in Alaska. The seas were rich with life. Plankton bloomed in the warm water. Fish populations exploded. Predators followed. But the Eocene was not static. Even as Basilosaurus swam, the climate was beginning to shift. Slowly, almost imperceptibly, the Drake Passage between South America and Antarctica was starting to open. Ocean currents were beginning to change. Cold water, rich in nutrients, was starting to circulate from the poles. The transition would take millions of years. But it had begun. The greenhouse was cooling. The age of shallow, warm seas was ending. And with it, the world that Basilosaurus dominated. What did the world look like when this giant ruled? The air is thick, humid, the kind of heat that clings to skin, that makes breathing feel like work. This is the late Eocene, 37 million years before present. The sun hangs in a sky that is recognizable but alien. The same yellow star, the same blue atmosphere. But something is different. The light is heavier. The air tastes of salt and organic decay. There is no ice. Nowhere. The Arctic is temperate forest. Antarctica is covered in vegetation, not glaciers. The poles are not cold. They are merely cool. The equator is a furnace, but life thrives there too, adapted to perpetual heat. Sea levels are high, higher than they have been in recent geological history. Shallow seas have invaded the continents. North America is split by a seaway that runs from the Gulf of Mexico to the Arctic. North Africa is submerged beneath the Tethys Ocean, a warm tropical sea that stretches from the Atlantic to the Indian Ocean. These are the sea where Basilosaurus lives. Not the deep ocean. The depths are still foreign to it. Basilosaurus is a creature of the continental shelf, of warm, nutrient-rich waters no more than a few hundred feet deep. The light penetrates here. Photosynthesis is possible. The food web is dense. The coastline is not like any modern coastline. There are no cities. No harbors. No boats. The shore is wild. Vegetation grows thick and tangled. Mangrove-like forests fringe the water. The trees are not mangroves, not exactly. Evolution has not yet produced those exact forms. But the ecological niche is the same. Salt-tolerant plants adapted to tidal zones. The land beyond is strange. Mammals dominate. Not the mammals we know. Not deer or wolves or bears. These are archaic forms. Early relatives. Some look almost familiar. Others are grotesque. There are horses, but they are small. Dog-sized. They have multiple toes, not hooves. They browse on low vegetation, wary, always watching for predators. There are carnivores too. Not cats or dogs, but creodonts. Predators with different lineages, different anatomies. Efficient, but not as efficient as the carnivores that would eventually replace them. The world is in transition. The age of dinosaurs is long over. The age of mammals is accelerating. But it has not yet reached the forms we recognize. This is an in-between time. A world that is neither ancient nor modern. Uncanny. Stand at the edge of the water. The sand is white, made from the pulverized shells of countless organisms. The water is clear but not empty. Even here in the shallows, there is life. Small fish dart between rocks. Crabs scuttle across the bottom. The substrate is alive with burrowing invertebrates. Inland, the forest hums. Not with the sound of insects we would recognize, though there are insects here. But the dominant sounds are birds. Not songbirds. These are larger, stranger. Some are flightless, descended from ancestors that survived the extinction that killed the dinosaurs. They are opportunists, scavengers, predators in their own right. Beaks adapted for crushing. Legs built for running. There are crocodilians too. Larger than modern forms. Dirosaurus, a giant crocodile with a narrow snout designed for catching fish. It basks on mudflats, eyes half closed, perfectly still. It is cold-blooded, dependent on external heat. The warm climate suits it. It has thrived here for millions of years. The water's edge is a boundary, a transition zone. The mammals of the land do not venture far into the sea. The creatures of the sea do not venture onto land, except for one lineage. The whales. They left the land millions of years ago. They are fully aquatic now. They will never return. Basilosaurus does not come to shore. It cannot. It is too large, too specialized. If it beached, its own weight would crush its lungs. It stays in the water always. Birth happens in the shallows, but the calf is mobile within hours. There is no crawling to safety. No terrestrial refuge. The ocean is both home and prison. The sky is vast. Clouds build on the horizon, white towers rising into the upper atmosphere. This is a wet climate. Rainfall is frequent. The coastal forests depend on it. The rivers that drain into the sea carry nutrients from the land. These nutrients feed the plankton. The plankton feed the fish. The fish feed the whales. Everything is connected. The ecosystem is a web, each strand dependent on the others. Remove one and the structure weakens. Remove too many and it collapses. The water is calm. The surface reflects the sky. Then, without warning, it breaks. Not violently. Quietly. A disturbance. Ripples spreading outward. A back emerges. Dark, smooth, not the rounded back of a modern whale. This is different. Longer. The dorsal ridge extends and extends and extends. 6 feet, 10 feet, 15 feet of spine visible above the waterline. This is Basilosaurus. The body moves in waves. Serpentine. The spine flexes, the tail drives downward, and the creature glides forward, barely disturbing the water. It does not thrash. It does not need to. The elongated body creates its own efficiency. Each undulation propels it smoothly through the warm sea. The head surfaces. The blowhole opens. A sharp exhalation, a mist of vapor and seawater hanging in the humid air. Then a breath. Deep. The lungs expand. Oxygen floods the bloodstream. The whale can hold this breath for 15 minutes, perhaps 20. Long enough to hunt. Long enough to dive. The skin is smooth, nearly hairless. Mammalian ancestry has left traces, whiskers near the mouth, perhaps, sensitive to pressure and movement. But no fur. Fur is useless underwater. Blubber provides insulation. Thick layers of fat beneath the skin hold heat, maintain body temperature, even in water that would quickly cool a terrestrial mammal. The eyes are small, set back from the snout. Vision is important but not primary. The water here is clear enough for hunting by sight, but Basilosaurus also relies on other senses. The lateral line-like structures along its jaw detect vibrations. The sense of smell, though reduced, still functions. The brain integrates this information, builds a map of the surrounding environment. The tail fluke breaks the surface as the whale dives. Horizontal. Wide. Not as refined as the flukes of modern whales, but functional. The downstroke drives the body forward and down. The water closes over it. For a moment, the surface is still. Then the ripples fade. The whale is gone, descending into blue-green shadow. Why such a long body for a whale? The answer is not entirely clear. Modern whales are compact because compact bodies are more efficient for fast swimming, for deep diving. But Basilosaurus did not dive deep. It hunted in shallow water, where maneuverability and slow cruising were more valuable than speed. The elongated body allowed for tight turns, for moving through kelp-like vegetation, for navigating reefs and sandbars. Or perhaps the answer is simpler. Evolution does not always optimize. It experiments. The elongated body worked. It was not a disadvantage. So it persisted. For millions of years, Basilosaurus thrived with this body plan. And then, when the climate changed and the seas cooled and the food webs shifted, it did not. Beneath the surface, Basilosaurus is a study in controlled power. Each vertebra is elongated, stretched beyond the proportions of modern whales. This gives the spine extraordinary flexibility. The whale can bend its body into curves that would be impossible for a dolphin or a sperm whale. The ribs are dense, thick pachystotic. In terrestrial mammals, heavy bones are a liability. But in water, density is useful. It helps with buoyancy control. Basilosaurus does not need to expend as much energy maintaining depth. The weight of its bones keeps it from floating too easily, allows it to hover in the water column without constant swimming. The forelimbs are flippers, small compared to the body, paddle-shaped. They are not used for propulsion. That is the tail's job. The flippers are for steering, for stability, for making minute adjustments in direction. They are remnants of the arms that once walked on land, now repurposed, reshaped by millions of years of aquatic life. The hind limbs are still present, but they are useless. Tiny femurs, maybe 8 inches long, embedded in muscle near the pelvis. There are tibias too, and fragments of what were once feet. But they do not extend beyond the body wall. They serve no purpose in locomotion. They may have been used in mating, for positioning or gripping. Or they may have served no purpose at all. Evolutionary leftovers, waiting to be selected away. The tail is the engine. The flukes are not as large as those of a modern blue whale, but they are powerful. Each stroke drives the body forward. The stroke is vertical, not horizontal. This is the signature of mammalian locomotion. Fish swim by flexing their spines side to side. Mammals flex up and down. This difference is ancient, encoded in the structure of the vertebrae, inherited from ancestors that ran on land. Basilosaurus does not swim fast. Not by modern standards. A dolphin can reach 30 miles per hour in short bursts. An orca can reach 35. Basilosaurus, with its long body and primitive fluke, likely maxed out around 15 miles per hour. Slow, but sustained. It could cruise for hours without tiring. The skull is massive, 3 feet long, perhaps more in large individuals. The jaws are lined with teeth, 40-50 teeth. The front teeth are conical, built for gripping slippery prey. The back teeth are triangular, serrated along the edges. These are shearing teeth. They can slice through flesh, crack bone. The bite force is immense. Not as powerful as a modern orca, but enough. More than enough. The muscles that close the jaw are anchored to the skull by massive temporal ridges. These ridges give the jaw leverage, allow it to generate crushing force. When Basilosaurus bites, the teeth penetrate deep. The jaws lock. The prey cannot escape. Compared to modern whales, Basilosaurus is primitive. Its fluke is less developed. Its brain is smaller. It lacks the echolocation capabilities of toothed whales. It cannot dive as deep, cannot hold its breath as long. But in the warm, shallow seas of the late Eocene, these limitations do not matter. Basilosaurus is perfectly adapted to its environment. It is the apex predator. It has no rivals. At least not yet. Hunger is constant. A 60-foot whale requires thousands of calories a day. The metabolism is high. Warm-blooded animals burn energy, maintaining body temperature. In water, which conducts heat away from the body far more efficiently than air, this cost is even higher. Basilosaurus must eat. Often, the primary prey is other whales. Smaller whales. Dorudon, a relative of Basilosaurus, about 15 feet long. Dorudon is common in these seas. It feeds on fish, on squid. It is fast, agile. But it is not fast enough to escape Basilosaurus. The hunt begins with detection. Basilosaurus patrols the shallows, moving slowly, conserving energy. It watches for movement. It feels for vibrations. When it senses prey, it changes. The body tenses. The tail strokes become more deliberate. It does not rush. Not yet. It stalks. The Dorudon is unaware. It is focused on a school of fish, darting back and forth, snapping at targets. Basilosaurus approaches from below, using the light filtering from the surface to mask its silhouette. The distance closes. 50 feet. 30 feet. 20. Then acceleration. The tail drives down hard. The long body whips forward. The jaws open. The Dorudon sees the movement, tries to turn, but it is too late. The jaws close. Teeth sink into flesh. The bite is precise, just behind the skull, severing the spine. The Dorudon goes limp. Basilosaurus does not chew. The teeth are for gripping and tearing, not grinding. It shakes its head, using the serrated back teeth to saw through blubber and muscle. Chunks of flesh separate. The whale swallows them whole. The throat is wide enough to accommodate large pieces. The stomach acids are strong, capable of breaking down bone. This meal will sustain the whale for a day, perhaps two. Then it will hunt again. Sometimes the prey is not Dorudon. Sometimes it is a shark. The seas of the late Eocene are full of sharks. Not the great white, not yet. But large predatory sharks nonetheless. Carcharocles, an ancestor of the megalodon. Otodus. These sharks are competitors. They hunt the same prey. They occupy the same niche. When Basilosaurus encounters a shark, the interaction depends on size. A small shark is prey. A large shark is a rival. Basilosaurus is not invincible. The sharks have teeth too. They are fast, maneuverable. A fight is costly. Injury is a risk. Infection. Blood loss. Weakness. Most encounters end without violence. The shark moves away. Basilosaurus continues hunting. Resources are abundant. There is no need to fight over every meal. But sometimes there is no choice. A carcass. A wounded whale. Both predators want it. Then the encounter becomes territorial. Aggressive displays. Jaws gaping. Bodies posturing. Usually one backs down. Usually. Basilosaurus is not the only archaeocete in these waters. There are others. Smaller species, less specialized. They feed on fish, on invertebrates. They are not competitors. Not yet. But evolution is relentless. New forms are always emerging. New adaptations. New body plans. The ocean is an arena. The rules are simple. Adapt or disappear. In a world this rich, what hunted the hunter? The answer is almost nothing. Adult Basilosaurus had few predators. The large sharks could theoretically kill one, but it would be a dangerous fight. Easier to target smaller prey. The real threat to Basilosaurus was not predation. It was injury. Disease. Starvation. Old age. But calves were vulnerable. Young whales, still small, still learning to hunt. They were targets. Sharks. Other whales. Even large crocodiles, if the calf ventured too close to shore. Mortality was high. Most calves did not survive their first year. But those that did grew quickly. Within a few years, they were large enough to be safe. Large enough to hunt. Large enough to continue the lineage. The ocean is not a void. It is a structure. Layers upon layers of life, each dependent on the one below. At the bottom of the food web is sunlight. Photosynthesis. Phytoplankton, microscopic organisms that drift in the surface waters, converting light into energy. They are the foundation. Without them, the entire system collapses. The phytoplankton bloom in the warm water. billions of cells per liter. They turn the sea green, sometimes brown, sometimes red, depending on the species. These blooms are seasonal, triggered by nutrients washing down from rivers, by upwelling currents, by the cycles of temperature and light. Feeding on the phytoplankton are the zooplankton, tiny crustaceans, larvae jellyfish. They are the grazers, the herbivores of the sea. They consume the phytoplankton in vast quantities. They, in turn, are consumed by small fish. Anchovies, herring, schools that number in the millions, moving as one, a shifting cloud of silver in the blue water. The small fish are prey for larger fish. Tuna, mackerel, predatory fish with streamlined bodies built for speed. They hunt the schools, striking from below from the sides. The schools scatter, reform. The dance is constant. Predator and prey locked in an arms race of adaptation. Above the fish are the whales. Dorudon, Basilosaurus, other archaeocetes. They are the top predators, the apex of the food web. They control the populations below them. They are, in a sense, the keystone. Remove them and the balance shifts. Prey populations explode. Resources are depleted. The system destabilizes. But the ocean is not only a food web. It is also a recycling system. Dead organisms sink. Plankton, fish, whales. They fall through the water column, descending into darkness. Scavengers feed on them. Crabs, amphipods, hagfish. What the scavengers cannot consume, bacteria decompose. The nutrients are released back into the water. They circulate. They rise with currents. They feed the phytoplankton. The cycle begins again. The late Eocene ocean is not dominated by marine reptiles. Those are long gone, casualties of the extinction that ended the Cretaceous. 65 million years ago, the mosasaurs, the plesiosaurs, the giant sea turtles, all vanished. The ocean was left to other lineages. Sharks, fish, and mammals. The whales are the inheritors. They evolved from terrestrial mammals, from artiodactyls, the even-toed ungulates. Their ancestors walked on land, browsed on vegetation. Then, for reasons still debated, some lineages returned to the water. They adapted. They diversified. By the Eocene, they have radiated into dozens of species. Some are fish eaters. Some are squid eaters. Some, like Basilosaurus, are whale eaters. This diversity is possible because the ocean provides niches. Different depths, different temperatures, different prey. Evolution fills every niche it can. The result is a complex, interconnected ecosystem. Fragile, resilient, constantly changing. Basilosaurus is a machine. Not in the sense of being mechanical, but in the sense of being engineered. Shaped by millions of years of natural selection. Every structure serves a purpose. Every organ is optimized for aquatic life. The respiratory system is efficient. The lungs are large, proportionally larger than those of terrestrial mammals. They can extract more oxygen from each breath. The blood is rich in hemoglobin, capable of carrying large amounts of oxygen. When the whale dives, its heart rate slows. Blood is shunted away from non-essential organs, directed to the brain, the heart, the muscles that need it most. The blowhole sits atop the skull, slightly back from the snout. This placement is not accidental. It allows the whale to breathe without lifting its head fully out of the water. Efficiency. The blowhole opens when the whale surfaces, closes when it dives. A muscular valve prevents water from entering the lungs. The brain is smaller than that of a modern sperm whale, but it is not insignificant. It weighs perhaps 2 or 3 pounds. The cerebral cortex is less convoluted, less complex. There is no evidence of echolocation. The structures that modern toothed whales use for sonar, the melon, the specialized nasal passages, are absent or primitive in Basilosaurus. But the brain is still capable. Spatial memory, pattern recognition, learning. Basilosaurus can remember feeding grounds, recognize individual prey species, adapt its hunting strategies. It is not self-aware, not in the way humans are. But it is aware. It processes information. It responds to stimuli. Hearing is one of the primary senses. The inner ear is specialized for underwater sound. Bones conduct vibrations from the water to the cochlea. Basilosaurus can hear low-frequency sounds over long distances. The groans and clicks of other whales. The movements of large prey. The rumble of distant storms. Vision is useful in clear water. The eyes are adapted for low light, capable of functioning in the dim blue haze of deeper water. But the eyes are small. Vision is secondary to hearing, to pressure sensitivity, to the integration of multiple senses. Thermoregulation is critical. Water conducts heat away from the body 25 times faster than air. A mammal without insulation would lose body heat rapidly, would burn calories just staying warm. Basilosaurus solves this problem with blubber. Thick layers of fat, sometimes a foot thick, insulate the body. The blubber also serves as an energy reserve. When food is scarce, the whale can metabolize its own fat. The skin is smooth, nearly frictionless. This reduces drag, allows the whale to move through water with minimal resistance. The surface is constantly being shed, replaced. Dead cells slough off, are carried away by the current. This prevents the buildup of parasites, of algae, of anything that might slow the whale down. Basilosaurus is a marvel of adaptation. But it is not invincible. It is vulnerable to disease, to parasites, to injury. A broken rib can puncture a lung. An infected wound can lead to sepsis. A shark bite can sever an artery. The ocean is unforgiving. Weakness is punished. Survival requires constant vigilance. Reproduction is slow. Whales do not produce large numbers of offspring. A female Basilosaurus likely gives birth to a single calf every 2 or 3 years. The gestation period is long, perhaps 12 months, perhaps longer. The calf is born tail first, so it does not drown during birth. It is large, already 12 to 15 feet long. But it is helpless. The mother stays close. She nurses the calf with milk rich in fat, 40% fat or more. The calf grows quickly. It must. The ocean is full of predators. Sharks, other whales, even large fish. A small calf is easy prey. The nursery waters are shallow, warm, protected. Sandbars and reefs provide some shelter. But there is no complete safety. The mother is vigilant. She positions herself between the calf and any potential threat. She does not sleep deeply. She rests one hemisphere of her brain at a time, keeping half awake, always listening. The bond between mother and calf is strong. Not emotional, not in the human sense, but instinctual, hormonal. The mother will defend the calf. She will fight. A female Basilosaurus, protecting her young, is more dangerous than a hunting male. Desperation makes her reckless. She will attack sharks twice her size. She will ram. She will bite. Often she wins. Sometimes she does not. The calf nurses for months. Gradually, it begins to eat solid food. Small fish. Scraps from the mother's kills. It learns to hunt by watching, by imitating. The mother is patient. She brings wounded prey to the calf, lets it practice. The calf strikes are clumsy at first. It misses. It bites too shallow. But it improves. By the time the calf is a year old, it is 30 feet long. Still small by adult standards, but large enough to be less vulnerable. The mother begins to spend more time away. She hunts for herself, lets the calf fend for itself. The bond weakens. Not abruptly. Gradually. Eventually, they separate. The calf is on its own. Survival at this stage is uncertain. Many juveniles do not make it. They starve. They are killed by predators. They succumb to disease. The ocean is not kind to the weak. But those that survive will grow. They will mature. They will reproduce. The cycle will continue. Mating is brief. Males compete for access to females. There are displays, vocalizations, possibly physical contests, though the evidence is unclear. The largest males likely have the most success. Size signals strength, health, good genes. Females choose, or males force the issue. Both strategies exist in nature. Both have costs and benefits. The act of mating is quick. The male uses the vestigial hind limbs for positioning, for gripping. This may be their only remaining function. A remnant of terrestrial ancestry, repurposed for a new role. After mating, the male leaves. He plays no role in raising the calf. Parental investment is the mother's burden. The ocean is not empty. It is crowded. Competition is constant. For food, for space, for mates. Basilosaurus is the apex predator, but that does not mean it is alone at the top. The sharks are the primary rivals. Carcharocles, a massive predator, 15 feet long or more. Its teeth are triangular, serrated, built for cutting through flesh. It hunts large prey. Whales, sea turtles, anything it can catch. It is fast, agile, capable of bursts of speed that Basilosaurus cannot match. When a Basilosaurus and a Carcharocles encounter each other, the interaction is tense. Both are predators. Both are used to being dominant. Neither wants to back down. They circle. They assess. Size. Condition. Aggression. Usually, the whale is larger. The shark retreats. But not always. A fight between them is brutal. The shark is faster, but the whale is stronger. The shark bites tears, tries to bleed the whale out. The whale uses its mass, rams, crushes. If the whale catches the shark in its jaws, the fight is over. The serrated teeth shear through cartilage. The shark dies. But if the shark avoids the jaws, if it can land enough bites, the whale weakens. Blood loss. Shock. The whale retreats. Or it dies. Most fights do not happen. The cost is too high. Both predators know this. They avoid each other when possible. They hunt different prey. They occupy different parts of the reef. Coexistence is possible when resources are abundant. Doruden is another source of competition. Not direct competition. Doruden is prey, not a rival predator. But Doruden is numerous. It feeds on the same fish that smaller archaeocetes eat. It occupies the same waters. When Basilosaurus hunts Doruden, it is regulating a population, preventing overpopulation, maintaining balance. There are other dangers. Parasites, worms that burrow into the blubber, into the muscles, barnacles that attach to the skin, bacteria that infect wounds. The whale's immune system fights these invaders, but it is not always successful. Chronic infections weaken the whale, reduce its ability to hunt, slow it down. Injury is common. A shark bite, a collision with a reef, a broken rib from a failed hunt. The ocean is full of sharp edges, hard surfaces. Healing is slow. Infection is likely. A minor wound can become a major problem. A major wound can be fatal. Even giants bleed. Age is the ultimate enemy. Basilosaurus does not live forever. 20 years, 30 years, perhaps 40 in rare cases. But eventually, the body wears out. The teeth wear down. The muscles weaken. The spine stiffens. Hunting becomes harder. The whale cannot catch prey as easily. It loses weight. It becomes vulnerable. An old whale is a target. Sharks sense weakness. They follow. They wait. When the whale is too weak to fight back, they strike. The end is not quick. The whale fights as long as it can. But in the end, the sharks win. They always do. Dawn. The sun rises over the Tethys Ocean, casting long shadows across the water. The surface is calm, glassy, reflecting the pale sky. Beneath, the water is dark, cold, relatively speaking. The whale has spent the night in deeper water, where the temperature drops, where the prey is less active. As the sun climbs, the whale rises. Slow, deliberate strokes of the tail. It surfaces. The blowhole opens. Air rushes out, a fine mist in the cool morning air. A breath. Deeper. The lungs fill. The whale dives again, but not deep. It stays near the surface, where the light is beginning to penetrate, where the water is warming. The hunt begins. The whale moves along the reef, watching for movement. A school of fish darts past. Too small. Not worth the effort. The whale continues. Patience is part of the strategy. Rushing burns calories. Better to wait. Better to find the right target. Midday. The sun is high. The water is warm, almost too warm. The whale slows. It rests. Not sleeping but floating, conserving energy. The body rises and falls with the gentle swell. The tail hangs down, motionless. Only the occasional flick of the flippers keeps the whale stable. Below, a Doruden swims by. The whale watches. Assesses. The Doruden is young, perhaps 30 feet away. An easy target. The whale tenses. The tail strokes. Acceleration. The Doruden sees the movement, tries to flee, but the whale is already too close. The jaws open. The bite is precise. The Doruden struggles for a moment, then goes still. The whale feeds. tearing, swallowing. The meal is over in minutes. The water clouds with blood. Small scavengers appear, picking at the scraps. The whale moves away, leaving the remains to the reef. Afternoon. The whale drifts in the warm current. The current carries it along the coast, past mangrove forests, past river mouths where fresh water mixes with salt. The whale does not fight the current. It conserves energy. It will hunt again later when the light fades, when the prey is less cautious. The sky begins to change. Clouds build on the horizon. The wind picks up. The surface of the water ripples, then chops. A storm is coming. The whale dives, descending to calmer water. The storm will pass. It always does. Night. The stars are out. The surface of the water is black, broken only by the phosphorescence of disturbed plankton. The whale surfaces. Breathes. The exhalation is quieter now, almost a sigh. The whale is tired. Not exhausted, but tired. It has eaten. It has survived another day. The whale descends into the cooler layers. Here, the water is darker, the pressure greater. The whale slows. It rests. Tomorrow, the cycle will begin again. Hunt. Feed. Rest. Repeat. This is the rhythm of life. This is existence. Simple. Brutal. Efficient. Above, the stars wheel slowly across the sky. They are the same stars that shine on the modern world. The same constellations. But the earth beneath them is different. Warmer. Wilder. Older. But warmth does not last forever. The change is gradual. Over millions of years. Too slow for any individual animal to notice. But the ocean remembers. In the sediment, in the fossils, in the chemistry of ancient shells. The late Eocene is ending. The greenhouse world is cooling. Antarctica, which has drifted toward the South Pole, is beginning to freeze. Ice forms on the highlands first. Small glaciers, then larger ones. The ice reflects sunlight. The planet cools further. A feedback loop. The ocean currents change. The Drake Passage between South America and Antarctica is opening. Cold water from the Southern Ocean begins to circulate around Antarctica. This isolates the continent thermally. The ice grows. The sea level drops. The shallow seas begin to drain. The continental shelves, which were flooded during the warm Eocene, are exposed. Coastlines retreat. The warm, nutrient-rich shallows, the habitat of Basilosaurus, shrink. The food web shifts. The plankton blooms, which thrived in warm water, decline. The fish populations change. Some species disappear. Others, adapted to cooler water, become more common. The prey base for Dorudon, for Basilosaurus, is disrupted. At the same time, new whales are evolving. Whales with different body plans. Shorter, more compact. Better suited to deeper water, to cooler temperatures. These whales are more efficient swimmers. They can dive deeper. They can hold their breath longer. They have echolocation, a tool that allows them to hunt in darkness, in murky water. Basilosaurus, with its long, inflexible body, is at a disadvantage. It is specialized for warm, shallow seas. It cannot adapt quickly enough. Evolution is slow. The climate is changing faster. The fossil record shows the decline. Basilosaurus remains become rarer in younger sediments. The species is retreating, confined to smaller and smaller refuges. The writing is on the wall, but the whales cannot read it. The coastlines are changing. The shallow seas that once stretched for hundreds of miles are narrowing. The reefs which provided hunting grounds and shelter are drying out, exposed to air. What was once ocean is now land. Basilosaurus populations are fragmented, isolated in pockets of warm water. The Mediterranean, the Gulf of Mexico, the Tethys remnants. These populations cannot interbreed. Genetic diversity declines. Inbreeding becomes more common. The populations weaken. The prey is changing too. Dorudon, which was abundant, is also declining. It faces the same pressures. Shrinking habitat, changing food sources. The smaller archaeocetes are disappearing. The new whales, the ones adapted to cooler water, are taking over. Basilosaurus tries to adapt. Some individuals move to deeper water, but the body is not suited for it. The long spine, the shallow water adaptations, are liabilities in the open ocean. The whale cannot compete with the new forms. It is outmatched, outcompeted. Reproduction becomes harder. The warm nursery waters, essential for raising calves, are disappearing. Females give birth in less ideal conditions. The calves are more vulnerable. Mortality increases. Fewer calves survive. The population ages. There are not enough young whales to replace the old. The decline accelerates. Not because of a single catastrophe. Not because of a meteor strike or a volcanic eruption. Just because the world is changing, and Basilosaurus cannot change with it. The niche it occupied is closing. The ocean is moving on. There is no way to know which whale is the last. The fossil record does not preserve such details. But there is a last whale. There always is. The final individual of a species. It swims alone. It hunts. It breathes. It does not know it is the last. It cannot. It is simply trying to survive. The population is tiny now, scattered across isolated refuges. A few dozen individuals, perhaps. Maybe fewer. They do not encounter each other often. The ocean is large. The whales are far apart. The hunting grounds are poor. The prey is scarce. The whale is hungry more often than not. It travels farther, searches harder. But the effort yields less. The calorie expenditure exceeds the calorie intake. The whale begins to lose weight. The blubber thins. The ribs become visible. The whale does not reproduce. There are no mates nearby. Or if there are, they do not find each other. The ocean is too vast. The population is too sparse. The species is functionally extinct, even if a few individuals remain. There is no drama. No final battle. No apocalypse. Just a slow fade. The whale grows weaker. It hunts less successfully. It rests more. One day it does not surface. It sinks. Quietly. Without witnesses. This is how most extinctions happen. Not with a bang. With a whimper. With a quiet failure to continue. The world does not stop. The ocean does not mourn. Other species fill the empty niche. Life continues. Just without Basilosaurus. The species lived for 3 or 4 million years. A respectable run by geological standards. But all runs end. All lineages terminate. Extinction is the rule, not the exception. Of all species that have ever existed, more than 99% are extinct. Basilosaurus is one more tally on that list. The body sinks. Slowly at first. The lungs still hold some air. The blubber provides buoyancy. But decay begins immediately. Bacteria in the gut start to break down tissues. Gas builds up. The body bloats. For a few days, the body floats. Scavengers arrive. Sharks, seabirds. They tear at the carcass, consume what they can. The skin ruptures. The gases escape. The body loses buoyancy. It begins to sink again. The descent is slow. The water is shallow here, perhaps 100 feet, perhaps 200. The body drifts with the current as it falls. It turns, rolls, propelled by the movement of water. It lands on the bottom. Soft sediment. Mud mixed with the shells of foraminifera, the skeletons of plankton. The body settles. The scavengers follow it down. Crabs, amphipods, worms. They consume the flesh. The blubber, the muscles. They work quickly. Within weeks, the body is stripped to bone. The bones lie on the seabed. Scattered. The current moves them slightly. Sediment begins to cover them. Slowly, a layer at a time. Months, years, centuries. The bones are buried. The sediment compacts. The weight of new layers presses down on the old. Water is squeezed out. The sediment turns to stone. Limestone. Shale. The bones are trapped inside. Mineral replacement begins. Groundwater, rich in dissolved minerals, seeps through the rock. Calcium phosphate, silica, iron. The minerals infiltrate the porous bone. They crystallize. Gradually, the organic material is replaced. The bone becomes stone. The structure is preserved, but the substance is changed. This is fossilization. Millions of years pass. The ocean floor shifts. Tectonic plates move. What was once seabed is pushed upward, becomes land. The fossils are buried deep, but they are moving toward the surface. Erosion does the rest. Wind, rain, rivers cutting through rock. The fossil is exposed. Perhaps in Alabama. Perhaps in Egypt. Perhaps somewhere else entirely. A fragment of bone, weathered, stained the color of the surrounding rock. Someone finds it. A farmer. A geologist. A fossil hunter. They recognize it for what it is. Bone. Ancient bone. They dig. Carefully. More bones emerge. Vertebrae. Ribs. A skull. They map the site. They document. They excavate. The bones are taken to a museum. Cleaned. Studied. Cataloged. The species is identified. Basilosaurus cedoides. The king lizard that was never a lizard. The whale with legs that could not walk. The fossil is placed in a drawer or in a display case, under controlled lighting, behind glass. Visitors walk past. Some stop. Some read the plaque. Some wonder what it looked like alive. We have returned to the museum. The air is still. The fossil is where we left it. Pale, heavy, textured with the memory of sand and sea. It has been waiting. It will continue to wait. Basilosaurus is gone. The species is extinct. The world it lived in no longer exists. The warm, shallow seas have drained. The coastlines have changed. The climate has cooled. New species have evolved. New whales. New sharks. New ecosystems. But the fossil remains. A fragment of a life that was lived millions of years ago. A reminder that nothing lasts. Not species. Not ecosystems. Not worlds. Everything changes. Everything ends. The ocean floor holds the memory of every giant that ever fell. Basilosaurus is one of many. Its bones lie in the rock, waiting to be found, waiting to tell their story. And when they are found, when they are studied, they reveal something profound. That life is resilient, that it adapts, that it endures for a time, but also that life is fragile, that it can be disrupted, that it can end, not just individual lives, but entire lineages, entire worlds. We are standing in the museum again. The fossil is in front of us. The vertebra, the weight, the texture, the sand. We can touch it if we are careful. We can feel the roughness of the mineralized bone. We can imagine for a moment what it was like when this bone was part of a living animal, when it flexed with the movement of a 60-foot whale, gliding through warm water beneath a greenhouse sky. But we cannot truly know. The past is gone. We can reconstruct it. We can study it. We can make educated guesses. But we cannot experience it. We are separated by millions of years, by extinction, by time itself. The fossil is all that remains. Stone, memory, evidence, a testament to a world that was and is no more. The ocean floor holds the memory of every giant that ever fell. But Basilosaurus was not the only titan to vanish. In the next entry, we will explore Dunkleosteus the armored titan, a world separated from the surface for far longer.